Okay, so this is the review session for the second exam in Chemistry 124, spring 2014. What I planned was, I don't know if you saw that sheet that I sent out. Okay, well, basically, what I want to do is cover mainly the quantitative stuff that you might have a problem with. Okay. I saw in the, when I looked through the chapters that you guys did some nomenclature. I'm not going to cover any of that. Okay, it's memorization. Frankly, those little rules I don't remember. Sometimes does. Anyway, but what I want to do is stick with the quantitative stuff. So you're in chapter 5, 6, and 7. And so, do you have anything you'd like me to work through in any of those chapters? You're the only one here. Whatever you want to do, we can do. Okay. You can pick a problem.
Okay. Well, let me go on mine real quick.
Yeah. Okay. Let's okay. So let's get to
now chapter 7. I don't know. I just maybe scatterbrained. I didn't even realize chapter 7 was on the test today, so I came in and like, oh, okay. So I started reading videos and stuff. So I'm a little hazy on some of that, and it seems like it's straightforward, but I could definitely use a crash course.
okay. So you want to crash course some of chapter 7.
Yeah.
Okay. The thing that would, if you haven't really studied it, the thing that most likely give you trouble in chapter 7 will be some of the later material, specifically molecular orbitals and second period elements. So molecular orbital theory, ideas concerning molecular orbitals, molecular orbital energy level diagrams. Okay. So let's just do one of those. Okay. You don't have a book.
No, I don't.
Okay, so one of the things you have to do is, I guess we make one is molecular orbital energy level diagram for a diatomic molecule in the second row. Periodic.
Okay. So,
I'd say your periodic table, you can see, so all the way from say, lithium to neon, you might want to make one of these diagrams later. So here's what you would do. So what we're talking about is talking about something new. So these are diatomic molecules. Let's just take the case of boron, carbon, for example. So what we're talking about is the molecule of boron, carbon, carbon. These are second row diatomic molecules. And so what you have to be able to do is make this energy level diagram.
what do you call them?
Yeah.
Oh, just two.
Right. Well, there's two atoms, but they're it's not just that they're diatomic. They're all the same elements. Diatomic doesn't necessarily mean you could have it's a homonuclear diatom. Heteronuclear diatomic would be something like you could have carbon and nitrogen. I'm not showing you that.
Right.
So now, let's think. So what happens is this: you're bringing atoms together and you mix the atomic orbitals and the molecular orbitals. So you have to know the atomic orbitals. So if you think about what are the atomic orbitals, you can go through, right? You have your 1s orbital, you have your 2s, you have your 2px, 2py, and your 2pz orbital, right? So all of the orbitals that are 1s, this is 1s orbital, there's a 2s orbital, and there's a 2p orbital that has the x, y, and z.
Yeah, right. The S's are just circular.
The S's are just spherical. Right. So and these are the ones that are kind of shaped like a figure 8.
Right.
So what you have to do is realize that if you look at the second row of the periodic table, you look at how many electrons are saved in an atom in the center. For example, oxygen has got 8 electrons. So that means that it has orbitals that are filled up in this manner. We start with the lowest energy, so we'll do 2 in the 1s, 2 in the 2s, right? So that means we've got what? 4 left. So the 4 left would have to be divided among these. Now, at the end of that row is neon. It has a total of 10 electrons. So there's enough room here for electrons. 2, 4, 6, 8, 10. Because each one of these orbitals hold 2. So let's just take an example of, say, boron. Say I'm going to bring these 2 boron atoms together. So boron, okay, is going to have a 1s orbital. Okay, so you have a boron over here. You have another boron over here. We're going to bring these together. And this is a boron. It's got a 1s orbital. What's the attitude of the orbital? How many electrons in the boron? 5. Right, 3 valence. So basically, what does this thing bring into the? Here's 2 electrons in the 1s orbital. Okay. This one's got, I'll just underline it. So there's 2 electrons in the 1s orbital. Okay. So that's 2. We got 3 more to account for. Well, then what's the next orbital? You got your 1s, you got your 2s, you got your 2p. Well, the next set of orbitals is going to be the 2p orbital. The 2p orbital. I'm sorry, 2s, 2s, right? 2s orbital. 2 electrons in each one of these. So now we've accounted for 4 of the 5 electrons. Now, let's just put 2p over here. And 1 electron, that's going to count for 5. Just going to get this out of our way. So this 2p. Well, let's put it down. Yeah, I really figured this out. So, all right, so okay, so you have a 2p orbital.
I think you have to put the eraser back.
Oh,
In the place. Otherwise,
the eraser's in okay, it's gone. Okay, so now you have this 2p orbital. Now, the 2p will be a comma. Can I erase the eraser? Why?
you try doing a circle with your eraser. Just trace out a small circle. And at the center. Doesn't matter.
Yeah, I don't know what's going on. this ratio will not go away. Maybe if I erase something with it.
I don't watch.
So back. Hold on. Okay, yeah. All right, it comes back. This is real problem coming back. I'm going to try the old escape button just to see what happens. Not a very smart board. Let me try some. He goes to the well, that's just turning the projectile is not going to change anything. So let me see something. Oh, I see. Okay. I mean, this thing should just.
What if you right click it and the
Is that thing projecting? Okay. 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 All right. I know. I'm starting to learn how. When this thing does stuff, like go with that computer stuff.
yeah.
And start finding stuff. So as soon as this thing's back up, I'll start finding. Okay, so you got a 2p overall to do it. Okay. And now notice that we've accounted for the 5 electrons. So now we're doing boron. So what happens is as you bring these atoms together, these orbitals mix. If you have 2 atomic orbitals mixing, you want 2 molecular orbitals. Okay? So one at a higher energy, and one at a lower energy. Okay? Right, so that's the mixing of two s orbitals. So off to the side here, say you had these 2 s orbitals and they were both had the same sign. Right, you're bringing them together, and then they along the bond angle, along the bond axis. Okay, you're going to make this region of electron density. Okay, so here's your boron. There's your boron nuclei right there. One boron nuclei, and there's another one. Okay, so that's a bonding orbital. Okay, this orbital is in lower energy than the original starting orbital. Now, you also, when you bring these things together, okay, if you bring them together and they're out of phase, in other words, one's a positive and one's a negative, okay, what that does is it forms an anti-bonding orbital. Okay. So there's the nuclei, and it kind of looks like this. It puts the electron density as a plane here, okay, with no electron density. That's at a higher energy. Okay, so those are what you have to realize. You make these bonding and anti-bonding orbitals in these simple systems like this. Okay, and the bonding orbital is in lower energy. So let's look at this and say we have these 4 electrons to divide up. So we're going to put 2 down here. Okay. Right. We'll put 2 of them down here. Okay. We'll put 2 of them up there. That accounts for those. Okay. Right. Now, what else do you have? Okay. You have I just got to move stuff around a little bit. Let's start it off fast. We just move stuff around. So,
Okay, no problem.
and usually what you do is you draw this. So now, we also had the 2s orbital. Okay? So on the 2s orbital,
You can probably tap the pen up at the top
oh,
left. Right
good thing you're here. Okay. That's all. 2s, we have 2 electrons. 2s, 2 electrons. Okay. I gotta get better. Admitted. So, okay, you have 2 electrons, right? So it does the same thing. I could redraw those diagrams, but they're actually the same, right? Because the 2s orbital, it looks just like the other ones, as far as I'm concerned. And so, what do we have? We have, I said there's 5, so now we got to take 2. You see how, so we've accounted for 4 electrons from each of these, from each contributing atom. Okay. These orbitals are called sigma orbitals because if you look down the bond axis, and you say you're on the bond axis, and you just look around like this, and everything always looks the same, in other words, it has rotational symmetry about the bond axis. You have to remember, a lot of what I'm saying, or most of what I'm saying about this geometric stuff, you really have to study the diagram. So it's a sigma bond. It has symmetry about that axis. So these when you anytime you bring 2s orbitals together, you're going to get sigma bonds, both for the anti-bonding and the bonding. So this is called like a sigma. Depends on what notation you use, okay? But it's like so it's a sigma 1s bond, okay? This is also a sigma 1s bond, but it's a star because it's an anti-bond. Okay? So what is this? This is a sigma 2s, and this is a sigma 2s star. All right, so that covers that. Now, what we didn't cover was the 5th electron. Okay? Because I made the drawing kind of big, what I'm going to do is go and start a new slide and do the 5th electron. That means we're still looking at boron now. We're in the 2p orbital of boron. And basically, there's 3 orbitals, right? Okay. So here's 2p over here. Okay. 1, 2, 3. And we know there's just 1 electron. Okay. So we have different orbitals that we can bring together. There's the px and py and pz. And how you end up drawing these things is a function of, first, one thing, how you define your coordinate system. In other words, because the energies, when you bring together, for example, this is a px, and this is a px, this is a py, this is a pz. How you bring these things together, they all aren't going to have the same energy once you bring them together. Okay? That'll be clear through the example. Okay. So we'll define our coordinate system as basically along the bond axis, that's going to be z. Up we'll say is x, and in and out of the board we'll say is y. Okay. So if you bring two P, okay, we're going to bring two PZ orbitals together. Why are these PZ orbitals? Because they're oriented along the Z axis. Okay, and we're going to make bonding numbers. This is plus, this is plus, this is minus. Okay, what will happen is you're going to get good overlap between these wave functions, and that's going to make this energy of the orbital that you make from that go down. Okay? There's an anti-bonding orbital also that goes up, but my point is that it goes up a great deal. Okay, so
Can you put the two S?
now go ahead.
I was going to say, can you put the two S inside the two P of the diagram, the same diagram together?
Well, you can, yeah. You just have to picture that this is on top of that.
Right, okay.
Yeah. So the point is that what happens is, out of bringing these different orbitals together, an energy level diagram will emerge. And the thing that you have to remember, as you're going to take the test tomorrow, is that from hydrogen all the way up to nitrogen, it's one diagram. When you get from oxygen and all the way to the end of that world, you do oxygen, fluorine, and neon, it's different diagram. And what I want to do is, I'm going to show you that diagram. This thing is smart. You know how to do it. Okay. So let's look at that diagram. So
The P and the S orbitals switch and you fill one with
Well, let's do, how about this? Let's do the most conventional looking one. The most conventional looking one is from oxygen and under the row. So for oxygen, fluorine, and neon, that's the one that looks the way you would think. Okay? And you'll see that'll become clear. So let's just do it like this. The 1s and the 1s coming together, that's 2s and 2s coming together, that's the same for all of them. The one where there's a difference, okay, we'll do them both on the same board. So this is a 2p, and there's an x, let me say x, y, z, and there's another one, okay, 2p, x, y, z, and we know what those are, you know how they look, they're oriented. I should not have gotten rid of this, okay? So this is z, this is x, and this is y, okay? Now, what happens is, from oxygen, fluorine, neon, like the last three things, when we bring these two together, remember we're bringing these two atoms together. What happens is, the z orbitals overlapping along this axis, okay? We're bringing these z orbitals together, okay? We're bringing these together, they have good overlap, and there's the largest really energy change compared to the other ones. So what you have is down here you have the two PZ orbitals together. So I'll just draw them like this. So these are coming together. So these are coming together, and we're going to make. Now, what you have to do is you have to look in your book and see how this bond looks, right? Because what it does is along the bond axis, right? The bond axis is like this. Okay? It gives you this region of high electron density, and you have these kind of loads that are associated with these outer phase parts. You got to study those drawings, because he could reasonably ask you to draw that, because that's not really a hard thing to draw. Now let me ask you quickly, is that a pi bond or a sigma bond?
Yep.
Here's a bond. That's the bond axis, right? It's a sigma bond, right? Yeah, because no matter where you're at, you walk down the axis and you look around, it always looks the same at that point.
Gotcha.
Okay? You would never be looking up here and then look here and then see something different. It is rotational symmetry. Okay? So So here it is. This is going to be, I'm just going to label this. You have to look at these studies and pictures. You need to be, you actually have to be able to draw this. It should be a, normally they make you draw this. So this is going to be a sigma, let's say 2pz. We just established that. Now, let's say you would bring, we're not looking at boron, we're just looking at anything from oxygen, fluorine to helium. In other words, 8, 9, 10 electrons. 8 from oxygen, 9 from each one. Okay? And so we're deriving this diagram. So now, this one's up here, and so of course, how would you label this?
Up there?
Yeah.
That would be sigma 2 star.
2 pieces. Right. Yeah, we're doing p orbitals. Now, what about orbitals, p orbitals along the x-axis? Right? So the nucleus is like right there. Okay? The nucleus is in the middle, right? So you bring these two together, and what happens? You get, here's the nucleus, you got a region of positive charge, or rather, that's not, you get a, here's a nucleus, Now above it, you get a region of positive. These are overlap regions, okay? You see that? Remember, the nucleus is right here in the middle. Okay? So when you bring these together, you get that. So that's the bonding orbit. Okay? And you should be able to draw that. Okay? There's an electron down here, there's an electron down here. And there's overlap, that's what we need. There's overlap, that is bonding. Okay? And only the same signs can overlap.
So it doesn't
The sign
end up looking like the PZ orbital in just a direction.
Well, it doesn't look like it at all. No. This is a different type of orbital. So this is going to be the, if you were going along this bond axis, okay, and you would stop anywhere in the bond axis and you were to look around, it would not have like rotational center, right? Because when you were looking up, you'd see this positive space. Positive is just a binary way of talking. You can say 1 or 2. You can say shaded or unshaded. Right? You look down, you see a negative space. That does not have local symmetry. In this case, since there's 2 lobes, it's a pi bound. So this is called, we would call this one then 2, rather a pi 2p, you tell me. Pi what?
Yeah, bond would be 2.
It's a pi
2p pi.
2px.
Yeah.
Yeah. So that's a 2px. Now likewise, this thing also has, if you brought these things together out of phase, right? Here, I'm drawing the nucleus. I'm making it a little better to see the nucleus. Right? This is positive, this is negative. It's a p bond. It's a px orbital, right? Okay. Negative, positive. You're bringing these together out of phase. Then you get something that looks like this. Here's the 2 nuclei, and you get these. Notice how there's really no electron density in between the bonds, in between the nuclei. Okay, the electron density's out here. That's significant. That signifies an antibonding orbital. It's a higher energy orbital. It doesn't contribute to bonding. So the point is that of all this is this. You should be able to bring together these S orbitals and p orbitals. You should be able to bring them together. You should be able to first draw a coordinate axis, draw the orbitals, bring them together, and draw what the result is. It's not that complicated. Right? It's kind of intuitive, right? So that's what you want to do. And likewise, if you were to, determine whether that's a sigma or a pi over, it's a pi over, right? Because it doesn't have, there's no rotational symmetry about the axis, right? So now, so that's a pi 2px.
Are all anti-bonds pi bonds then?
No, I mean, no. No, I mean, here's an anti-bond that's not a pi bond, right? The first one we derived, and we brought them together along the z-axis, right? So no. Okay. So now, the thing about the other one, the y, so if you had things, now we're trying to draw into the board, right? It's kind of problematic, right? It's kind of hard to draw into the board, especially when you're not much of an artist, right? But do you see how you get this result, only it would be flipped, right? Okay, and you get this result when you brought them together out of phase, only it would be flipped. Okay, in other words, I could just do this. If I were to, I'm going to get rid of this. Right? If I were to just change the labels of these axes. Now, I made this y, I made this z. These are now the py orbitals. But you see how they look the same. They just flip 90 degrees. Right? Okay, so that's why when you bring them together, they make the same, they have the same amount of overlap. Therefore, they result in the same energy. These things are meant to be drawn. So this is pi 2py star. Okay? And this is pi 2py down here. Okay? Do you see what happened? Like the ones that had strong overlap, they split the energy, the z, when we brought the pz orbitals together. There's a much greater splitting of energy. Right? Okay, this is deeper, more stable. This is more unstable. The x and the px and py, when we brought those together, okay, those don't overlap as much, and the energy difference of the orbitals between the counterorbitals is not as much. Right? Okay, so it's easy. Once you make the drawings and go through that yourself, it's very easy for you to remember the 2p part of the drawing for oxygen, chlorine, and nitrogen. Okay, in other words, that applies when he gives you this. He asks you to throw in the energy level diagram for this stuff. Now, you and I are going to do that right now. Oxygen's got eight electrons, so each oxygen is bringing eight electrons total. We know that when we looked at this, we know here's how much we could take up just bringing the 1s and 2s together. 2, 4, 6, 8. Right? Okay. Now, but we have 16 electrons to deal with. There's 2. So let's deal with it. This will be kind of the education. Okay? So let's do it. We need to put 8 electrons in. Where are they? Let's just make sure we got them on here. In these 2 p orbitals. How full the oxygen p orbitals have 1, 2, 3, 4. And so 1, 2, 3. Okay, so you fill these up a certain way. 1, 2, 3, and then you pair them. 1, 2, 3, and then you pair them. It doesn't matter what they show. So the point is now, what are we going to do? We have 3 here, we have 3 here, that's a total. We have 4 here and 4 here, that's a total of 8. So what you do is you go down to the lowest orbital energy first. It'll be 1, 2, 3, 4, 5, 6, right? No. So this one. 5, 6, right? 7, 8. Now, so the question you get then is and this could be drawn. Actually, this should just be drawn. usual to draw these like this. Now, what is it that you notice about this? You have two unpaired electrons. It's important that you realize that you wouldn't pair these up. That's a higher energy configuration. If I put them both there, even with, of course, the other one would have to spin down.
Right.
You could not have them both spin up, because then you violate the Pauli exclusion. So here they are distributed among these orbitals in the lowest energy layer. You notice you have two unpaired electrons. When you have unpaired electrons, you have to think paramagnetic. In other words, this can interact with the magnetic field. Okay, you know what that means. Yeah. Okay, so it's paramagnetic. This is important that you know. Another thing is you want to know what's the bond. If they're down here in an energy level below the contributing energy level of the atomic orbital, these are considered bonding orbitals, right? Because if you take any given electron here and here, where it ended up down here, if it ended up down here, that is a lower energy than these two together. So you could just do a geometry. Right? So now that means these are bonding electrons, bonding orbitals. Okay? So one thing you do is you calculate something called the bond orbital. You calculate the bonding electrons and the antibody. You subtract one from another and divide by 2. So let's do that. 1, 2, 3, 4, 5, 6. 6, 9, 2, 4. It's 2. And as you know, oxygen has a double bond. Remember the Lewis structure of oxygen, right? You have this. Those are pairs of electrons. Okay, that's the Lewis structure of oxygen.
So the double bond, first bond, sigma bond, second bond, pi bond.
Yeah. First bond's a sigma bond, the second one's a pi bond. And why is that? Well, you can tell that this makes a sigma bond. We brought those two PZs together, right? It was a sigma bond. We demonstrated that. Okay? And it's in lower energy than these pi bonds.
Could I ask this, would it be wrong if you had the X on the bottom and
It doesn't matter. It has to square. It has to reconcile with the coordinate system that you drew. In other words, the z-axis is along the bond axis. Okay? If the z-axis wasn't on the bond axis, then the diagram would be wrong. Okay? It's arbitrary. Your choice of axis is arbitrary. And furthermore, your choice of which dimension you want to show the bond axis is arbitrary. But customarily, what you do is you use a drawing like this one, and you get the bond axis to z-axis. But, I mean, there's all kinds of ways you can be tested on this material, right? He could just give you a different, you could label this different, and say, okay, now properly label this, and you would have to know.
So if you started with Y going on,
Yeah.
right, then I would start with Y.
That's correct. And you know that because you already know how to think about it. You have a bond axis, you know how to draw the orbitals, you know what happens when they come together. If you haven't like looked at the study of the picture, in this book, do you have a copy of it?
I do not.
Okay. Well, okay. So you really have to study those pictures. They're intuitive, right? They're not going to be this is a big deal, but it's a memo, right? They just make sense. So you got it. If you change the coordinate system, then you have to change the way. So now, but there's a physical reason why this is a lower energy, right? Because when you bring them together like this, there's much better overlap than when you bring them together like this. Okay? It may not look like it, but it's true. Okay? All right, now, so let's move on to fluorine. Fluorine's got 9 electrons total. So we have to count for 18 electrons. So that means we just got to add 2 more to this thing. 1. Because oxygen had 8, now we have 9. I'm doing oxygen for you and me first, right? That's what I'm doing. So that means, you got this, right?
Right.
What's the bond order?
You have, 2 million, so it's, 246, minus 4, 2, right, so 1.
One, yeah. And so fluorine, if you call the blue structure, is just a single bond in each pair of them. Fluorine gas.
Right.
And of course, you look where fluorine is, it only needs to gain one electron to have it in operation. So fluorine, chlorine, bromine, iodine, those things. That's kind of the top. This diagram now. Right? So now, neon has how many electrons?
Right.
So that means I got to put an electron here, right? And I got to put one here. That's what they're bringing to the table.
Right.
And then I got to put in 2 more electrons here. Right? Now what's the problem? It's zero. Right? You never see it. Right? This doesn't exist.
Right.
So that's it. Now, we did oxygen, fluorine, neon. Now, the other ones, there's an issue. What happens with the other one? This energy level here, this 2pz, all you got to do is remember that this will go up. It gets moved to up here. In other words, the lowest energy ones are then these. Okay? And this one's up here. It's still bonding, right? It's still lower than that. Now, why is that? It's because with the smaller molecules, or with the smaller atoms rather, these orbitals, these 2pz orbitals, are interacting with the lower s orbitals, 2s orbitals, and it kind of lowers the energy of the 2s and raises it to the 2pz with this diagram. Okay. You understand? So memorizing this diagram. Here's the diagram you actually have to know, right? The first, the top one is for the case that we want to do first. It's showing the 2s and the 2s. It's not even showing. Yeah, it's simple to memorize, right? If you just think oxygen, fluorine, and neon is normal, you want to do that. This one is not normal. So it's only relevant. It's only relevant. To, so it's only relevant. Carbon, yeah, carbon would be active carbon. So the only time it's relevant is nitrogen. Well, it could be relevant. You might want to relevant talk about exciting electrical. So it could be relevant in carbon. Like I said, it talks about exciting an electron to a higher level. You'd have to say the next level would be whatever. All right, so this is what you have to remember. It's going to ask you to be able to draw those. I didn't talk to them, but I know from. I don't have any inside information, but I know these tests, that's typically what's done. If you covered that material, then these diagrams you want to really be able to be quick with these. You want to be able to make those labels, sigma, pi. You want to be able to draw the two things coming together, and how they look. Okay, a bonding orbital, anti-bonding orbitals. You want to be able to draw all those. And you want to be able to take the electrons, fill them in. You know, do some fictitious model. And a fictitious energy level diagram. Say, now, tell me what the bottom is.
How would oxygen and hydrogen?
All right, well, so now you have to mix orbitals.
Right.
Okay? And orbital mixing occurs when, first of all, the orbitals have to be close to energy. And so they usually will do sort of a qualitative. Let me just tell you what So we just started doing it. So what happens is this, let's just do a hypothetical. So let's say you have a 1s orbital on some species here, and you have a 1s orbital on another species. So this is 1s, and we'll just say that both of these are filled. Now, you'll notice that I didn't draw these on at an equal level, because it's implied that the y-axis here on the board is the energy. Right? Okay, so one is at a lower energy than the other. The thing is, they have to be near, they can't be too far away in energy, they don't mix at all. Okay? And so usually the kind of problem you would get would be, it would be told to you, or it would be implied somewhere that they're going to mix with that.
I didn't read this chapter in detail, so I would have to go through it and see how they treated these things. I'm just giving you kind of a picture.
And so, let's say they mix. So they mixed, you're going to have an antibonding orbital here and a bonding orbital here. So it's the same, it's basically the same thing. Now, in order for them to mix, they have to have their symmetry considered. For example, let's say you could ask for something like this. Right. Here is a p orbital, here's a p, I'll draw a coordinate system. X, Z, Y, so here's a px orbital, and there's a nucleus. Let's say you have a one s orbital, something like 2s orbital, or 2s orbital, right, which is symmetric, and there's a nucleus there. Okay. So if you brought these two together, there'd be no net overlap. So they couldn't mix. In other words, you couldn't draw this diagram. You couldn't mix the 2 x with the 2s orbital. Okay, because look at the way they're going to line up.
So doesn't the 1s from the oxygen mixed with the 1s? Is that how they?
Well, I mean, it depends. It would depend on what we're particularly looking at. The thing is, you have to look at the specific. You can't look at kind of case by case. It's not really something. I mean, if I looked at this all the time, I would know. It's not something that there's just this. Okay. But the point is, you have to also realize that you can't just. There's symmetry considerations. Right? Because if I mix these together, what would happen if I brought these together along this axis? Okay. Positive and the positive, okay, that would be considered overlap. The positive and negative, that would be considered negative overlap. Okay. So that if you were to take, conceptually, if you were to take a p orbital, okay, and just put an s orbital on top of it, this, there's 0 overlap. So it cancels. Wouldn't matter. So this is plus. It would overlap with the plus. But it would have essentially negative overlap. Negative. So that would be the whole thing would be 0. So in other words, there is no mixing. These aren't going to form a bonding or antibonding. Okay. So this is another issue that might come up. Okay. You can't just. The point is that for things to mix, they have to be near each other in energy, and then there's symmetry considerations. So you have to look at that. You go over that in your mind. Not everything can mix with everything. That's the case where they just cancel out. So, but what you should do is, what I would do is look at what they might have said about. Basically, what you're mentioning is a heteronuclear diatom. What might what we did was we looked at homonuclear diatomics.
Then there's mutual heteronuclear diatomics. For example, I'm looking at page 91, and he's doing carbon monoxide. And he's showing that the 2s orbital on carbon is mixing with the 2s orbital on oxygen. Okay. The 2p orbitals on oxygen are mixing with the 2s orbitals on carbon.
These things, you can make essentially a gas of what, but I don't think it's going to have anything like that.
But I would carefully use this. It's even too much. There's only one page.
Yeah, it seems pretty straightforward. I think for this chapter, the homework I know is it's considered short. It would not be fairly intuitive because he just covered subject. Yeah.
Well,
That's
did you see the lecture thing?
yes, I did see what.
Energy level diagram?
Yeah, he went over it, but it was the first time I saw it, the only time I saw it.
Okay.
Yeah, this helps. This solidifies some of what he said, and maybe it's new information that simply was
Okay. So
I got a pretty good grasp of it.
you want to be able to draw orbitals, you want to be able to picture them coming together and say, that line and main line. When the two pluses come together, they're going to overlap. That's fine. Plus and minus going to come together. So you want to be able to draw those. You want to be able to distinguish the sigma bond from a pi bond. Okay? You want to know those two molecular orbital energy level diagrams. You know, you should be able to just, when I took it, I just drew it right away. All it is, it's simple.
Right.
You should be able to draw it right away. Put your coordinate system up and label it. Right? The whole thing. Just right away you should. So, how about anything else from the earlier chapters?
I'm taking over this.
I'll tell you something, some stuff in chapter 7. There's a lot of qualitative stuff in it. It's nice to pick up on it, carefully read it. Maybe not. That stuff you gotta kind of read. Not really quantitative. So, what about chapter 6?
Okay, so chapter 6, I got hung up on turning what molecules are forward. I think I got it now.
Oh,
But
well, the polarity you want to look at it, page 7.
right.
For example, if you had a molecule, let's say, ethane, okay? This is ethane. So, let's just start with something more basic. I mean, if you had oxygen, you had a polar molecule. What makes something polar is basically how the electrons get distributed among the atoms.
Yeah, so that's the 8 2 4s and 2 12 left. So it's not full.
Well, it's not polar because it's symmetric, right? There's an equal distribution of charge on it.
Yeah.
Whereas when you get when you have different atoms, then
You can have an issue of polarity. So, for example, now the way you make these judgments is you look at electronegativity. And so, hydrogen is on an electronegativity scale 2.1, carbon's 2.5.
so on this bond here, more of the electron density would be towards the carbon. They don't share the electron density. They're linked by sigma bonds, right? But they don't share the electron density equally. So if you were to look at this in isolation, okay, this is polar.
Right.
It's not very polar, but it is polar. Okay? But if you look at the molecule in total, it should be clear that all these polarities are canceled, right? Because of symmetry. In other words, this is going to cancel with that. Over here on this bond is going to cancel with something over here on this bond. And likewise with these two. Right? So symmetry is huge. Now, if you have something like
If you have something that's clearly added on lack of symmetry, then you should be able to.
should be readily apparent to you that the thing is going to be polar. Right? So let's look at HCl. Okay? So HCl is a lot of electron density over there. Okay? The bond itself is what we're talking about. Look at the, you know, should become familiar with electronegativity. You don't need to know the electronegativity to know this. Right? So it basically would be like this.
I mean, electronegativity,
As you move across the table, it goes up, across and out, across and out. So you want to know that, you want to kind of look at that all in electronegativity scale. I'm on page 243, so it shows me. And so that's really what, judging whether something is polar or not. Is there an electron charge distribution on the bond? It's not evenly distributed. And in reality, if you have two different atoms, it's not going to be evenly distributed. But then you have to look at the molecule as a whole. Where all those vectors cancel each other, they cancel each other. So that's not going to be polar. Any other questions about that? No.
Polar, that's actually pretty good.
Yeah.
Chapter 5 is also covered.
Yeah.
Chapter 5 is more like calculation. Here's one. Determining empirical formula from combustion analysis.
Yeah.
You did anything like that? Those are fine.
no, it was fun. Yeah, we should go over it if you don't mind.
Why would you do it?
Yeah, I had, did have some trouble.
Okay, so I'll just go over the example.
So it says vitamin C is essential for prevention of scurvy. Combustion of 0.2 grams in the sample of this carbon hydrogen oxygen compound yield.
What they do is it takes 0.2 oh, okay. You got it. So you measure out a certain amount of the sample, right? And then you do combustion analysis. So basically, you burn it. And they tell you that this is carbon, hydrogen, oxygen compound. So if you're going to burn the sample, so you got the sample in here, right? So this is the sample, and you're going to hit it with oxygen in order to burn it. So here's your sample in here. So what's going to come out? When you combust something, what are the combustion products? When you totally combust just a carbon hydrogen compound or a carbon hydrogen oxygen. It's all going to be, CO2, okay, plus H2O. Right? Now, if I only feed in oxygen, okay, and carbon and hydrogen come out as well, that means they had to have come from the sample. Okay. Now, I fed in oxygen, but we know that the sample also has oxygen. So unless I kept very careful care on how much oxygen I put in and how much unconsumed oxygen came out, there's no way that I could determine how much oxygen is actually from the sample by analyzing the products, right? Okay. You can know how much water came out, you can know how much CO2, then you'd have to know how much oxygen went in, exactly how much was consumed. So it's not really done that way. What's done that way is you're going to get this amount of carbon dioxide is going to be known. So the amount of carbon will then be known. Right? The amount of water will be known. So the amount of hydrogen will be known. Okay? So then what that means is, if you know you put 2 grams of sample in, ultimately, okay, oxygen comes from a mass balance. Okay? That makes sense, right? If you put in something that's made of carbon, hydrogen, and oxygen, and you know how much carbon came out, how much hydrogen came out, you know how much total mass you put in, then the mass that didn't come out, or that you can't account for whatever reason, that must have been oxygen. Okay? So that's how that works. So what do they tell you in this?
They say carbon yields 0.2998 grams CO2.
So you have 0.2998 grams CO2. You've got grams of CO2, you're going to want moles. You want moles of carbon. Okay? So you just take the molecular weight of carbon, grams per mole, right? So I just put molecular weight of CO2. It's not molecular weight of carbon, molecular weight of CO2, right? And that's going to give you moles. Right? Grams divided by grams per moles gives you moles. CO2. You know that there's 1 mole of carbon per mole CO2. Therefore, moles CO2 equal moles carbon. Okay? Now let's just say we know we have a moles carbon. Let's just say it's X. Okay? So we're not going to do the calculation. Well, actually, since they're already done in the book, I'll write down. In the example problem, they actually did.
So that gives you 0.006812 moles carbon. 0.0068.
Moles. Okay. Now, you do the same calculation with the water. Right?
They tell you how much. They tell you at 0.0819 grams H2O. 0.0819.
So all I have to do is put 0.0819 grams H2O divided by the molecular weight of H2O. Right? And you'd have moles H2O. Right? Now, so here's the thing about that. You have to be careful. They tell you that.
So they do the calculation all. The point I wanted to make was there's 2 moles of hydrogen
Per mole of H2O. Right? So if you calculated 10 moles of H2O, then you had 20 moles of hydrogen. You can't forget the stoichiometry.
Right. And so the final answer is 0.00909 moles hydrogen.
0.009
09 moles hydrogen.
So now, all we have to do is take the molecular weight of carbon, multiply it times the moles carbon, right? So moles carbon times molecular weight of carbon, moles and grams per mole. We want to get oxygen, so that's what I call it. Moles of carbon times grams per mole gives you grams carbon. Right? You calculate the moles hydrogen, right? And the molecular weight of hydrogen. hydrogen. Right? So then, 0.200 minus these two is carbon and hydrogen. It's going to give you grams oxygen, right? Right? Yeah. Okay. So then take grams oxygen divided by the molecular weight of oxygen, which is grams per mole. Gives you moles of oxygen in this 0.200 gram sample.
Can they tell you what the moles oxygen is? 0.1090. 0.1090.
Yeah. So here's all this stuff. Now, if we want to calculate the mass percent of everything, it's simple. We know that the total mass is 0.2, and we know the masses of everything. So mass percent of carbon is just take the grams of carbon divided by 0.2, multiply by 100, that's that. Mass percent, mass percent. What else did they ask me?
What are the mass percent? Oh, anyone want empirical formula. What empirical? In other words, they want the ratios of carbon.
Right. That's what empirical is. It's just the ratios of the elements. So how do you do that? Well, you divide by the lowest number. Right? So that right away is going to give you, if you divide carbon by, carbon is the lowest number, so then this would have a 1 down here. This looks like it would be a 1.3 or something for hydrogen, okay? Approximately. And then this one looks like it's 100. Would that be right? 10 times. This is almost 1 times that, like 10. Does that make sense? I'm just doing it in my head. So
Very good.
When 006, 009 by that, 006. You can talk, you get the real number.
So we're dividing 0.109 by 0.006, right?
Yeah. Why divided by the wrong thing?
Yeah, 15.99.
15.9.
Yeah, 0.965.
15, so 16.
Yeah. And that's,
That's a nice, I think I might have read the wrong number.
Point. Oh, no. Point. 006 equals carbon and moles of oxygen. Oh, so moles of oxygen is 0.006.
That's, I mixed up mass, moles. Okay. I knew something didn't look right. It's,
yeah, it was quite a lot of oxygen.
0.0068.
right, couldn't be. 0.0068. So what are our numbers now? They're basically 1
So basically, yeah, one.
for carbon.
Carbon to oxygen is one.
Okay.
So this is 1.00015. That's one.
Okay, so 1.
And then hydrogen. So 1.2.
Yeah, okay.
Right. So,
We're not done yet.
then those numbers multiplied by 2.
Yeah. So if you multiply it by 3, you want the lowest set. Which, if you went too big, it would be easy to see. Like you did multiply it by 6, you'd say, hey, I'll divide that by 2. So now you have 3, hydrogen's 4, and oxygen is 3. And you do that.
And so now, if you do the molecular weight of vitamin C, you could actually,
Adjust these numbers, right? 'Cause I don't think vitamin C has just got 3 C's, 4 H's, 3 O's. Obviously, larger.
Right.
And so what you would do is you would calculate the molecular weight of this fictitious molecule. Okay? Right? Say this was, let's just make it up, say it was 10. If you look at the molecular weight of vitamin C and it's 100, then you just multiply everything by 10. And so that would be 30, 40, 50. So straightforward. So now, what happens when you change that? What happens to remember when I was using it? I found something. Where did that go?
Oh.
Yeah, actually,
Oh, okay.
it actually, in PowerPoint, it dumps a tab. I wouldn't have thought that it would do that. All right, so do you see anything else in there? Anything else you see in there of interest? Quantitative stuff?
I think I really need to do a lot of communication on the polyatomics. Cram goes into the quiz,
polyatomic,
like memorizing how to handle what we're supposed to.
oh, polyatomic cations and anions.
Yeah.
I'm looking at page 193. You're supposed to memorize that.
Yeah, like acid.
Yeah.
Cyanide. And I remember pretty well, but that I'm remembering the chart.
Can you tell you what you give us?
No, there's a practice exam. How many atoms are in a sample of carbon monoxide? I mean, much as easy because you go through the weight, molecular weight, but that's how many moles you have.
You just know that for
One multiplied by, what did it say? Something like that.
well, let's say you have a compound, right?
Yeah.
You know how many moles of the compound you have. So if you had a compound of methane, C2H6, if I tell you you have 10 moles of methane, how many moles of hydrogen?
Wait, I'm sorry, we could put it together.
So that's methane. Let's say that's methane.
So we're 1 mole of that.
So those lines are hydrogen.
Right.
If I tell you you have 10 moles of methane, how many moles of hydrogen?
So
It's just easy.
and multiply that by 6.
What are you talking about?
For how many atoms?
Well, we just said moles, right?
Right.
Okay, so if I tell, all right, so and then he says how many atoms you have, okay, well, you just have to remember, 6.023 times 10 to the 23rd, anything in all of anything. 6.023 atoms per mole of atom. So if you had 10 moles of this, and you had to you had to convert that to how many atoms do you have, right? You just write 6.023 times 10 to the 23rd, right? Atoms per mole, right? Moles would cancel. You have this huge number of atoms that you expect. Okay. So does he make you memorize stuff for the exam? Or do you have to memorize overhand?
Uh, yeah, we're supposed to memorize the diagrams. That was for the, I'm assuming in the test, this is the end, let's see, this is lithium phosphate. Li3 QO4.
QO4 is 3 minus, which is plus.
So lithium is plus all the way.
What you have to do is remember that for the first row of the periodic table, all of those only make plus 1 atom. They don't make plus 2. You see that lithium, sodium, potassium.
Oh, yeah.
They only have 1 electron. And then beryllium, magnesium, calcium, they always make plus 2. They want to lose 2 electrons because of the balance check. They don't like to use just 1. There's no calcium. There's calcium 2 plus. There's no calcium 3 plus. Electron from the argon, which is very stable. Looking at the periodic table.
Yeah.
So that, and those should be, you want to no, does it give you a periodic table?
Yeah, I mean, they're up in the classroom.
Okay, so you can't get that wrong. Right? You've got to know there's no lithium 2 plus.
Right.
And there's no calcium. So those are what else?
Yeah, like here, right, chemical formulas for magnesium, cover that, and rubidium nitride.
Okay, well, that means that there's definitely some memorization involved.
Yeah. So, yeah.
How'd you do on the first
I got a B, got a high B. Oh, no, sorry, I got a look.
one? Surprised there's not more people.
I'm shocked because there are a lot of people who, I mean, maybe it's just the time that the society is are a lot of people who are not doing well. I mean, I answer a lot of questions in my class. There are a few others who I think are really positive, less than I am, but quite a few. Yeah, I think, I mean, what I'm seeing so far, I feel like we've gone over the stuff that we need to, the other stuff, which is just a matter of observation. As well as something that I have to figure out. What's the oxidation state for?
So, let's look at the complex. So, now, there's a set of rules and sign activation. You want to work together enough times, the common ones. The rule is pretty much proportional. Activation is so if you go to page 107, seven rules for sign activation. This is something you definitely want to know. You well understand. You really want to work with that enough times to unfortunately. We'll do some examples here. Page 186 when we start. Typically, it's a set of rules to some extent. All the compounds to the same extent. Electrons and bonds. Not all of them. Bromine, two bromine oxidation material. But when you join other things, as a, for example, hydrogen fluoride, you could assign all the entirety of the, it's called the electronegative fluorine to the negative charge of that fluoride. So you can, just as a formal matter, you could say all of the charge of one electron. And so this has some usefulness later on. So the thing is, there's a set of rules that help you decide. And they're not like just intuitive rules that you do and not they have. So, are you on CK 5?
Oh, I don't have the book.
Okay. All right, so
as you're looking over here,
I mean, what is
atoms
described-
are elemental from oxygen.
what is it?
They're all zero in their elemental form.
Right.
Monatomic ion, lithium plus, and plus, I guess it's sodium plus acid plus 0 plus 1. Everything in the second column group would be plus 2. Everything that's not one of the halogens under it, that's group 7. So -1, iron plus 2 and iron plus 3.
So a lot of it, you have to know, so and this is like a formal way of dividing the charge. And you just have to memorize the rules. There's also some of these, like you mentioned, iron. So a lot of the compounds, the way you, because the transition metals, they can have multiple oxidation states, right? Yeah, this is an important point. They can have multiple oxidation states. So you know there's no, you don't see it's just a rule in there about it. It doesn't say all 3D metals are in this oxidation state. And so how do you determine the oxidation state of transition metal?
By what they're bonded with.
Yeah, well,
used to do a charge balance,
Yeah.
because let's say you have,
Let's pick a complex iron. No, it's not. It's not with the charge. What is it? What is it called?
He's got the copper carbon oxygen.
You got?
CuCO3, so copper carbon.
Oh, CPCO. That's not, doesn't have any charge.
Well,
That's copper carbon.
he's
let's do that.
well, on this one, it's determining the oxidation number of each element in the compound.
Well, let's do that.
So, uh,
This will illustrate the plan.
oxygen typically is in 2.
Right, unless you see hydrogen peroxide, then oxygen is negative 1. It'll watch it. But almost all, and he'll throw something like that. They usually do.
Right.
Almost all of them, in almost all cases, oxygen is negative 2. So this would be 3 times -2 is -6, right?
Right.
Carbon is usually what?
I want to say +4.
So if you have copper is 4. What does that tell you? It tells you that -6 plus 4, it's got to be plus X, it's got to be 0, right? Because the double charge has to be 0. That's just a simple matter of algebra. It's got to be +2. So the thing is, you have to memorize all those. Just go through. They're easy to memorize because you do so many of them. It just comes. But the thing is, there's always these ones where you're going to have to do a mass charge balance together. This copper could exist in
More than one oxidation. Two, multiple copper, 1, 2. I think it's kind of that. Okay. But pointing. So now, anything else in there that is?
Let me see. He's got 25 problems on the practice exam.
Did you have that exam?
Yeah. I'm going
Well, it's nice that he gave you practice.
Yeah. Yeah, the structure.
Yeah, you don't understand the basics.
Yeah.
You could go in for an architect in most cases. There's exceptions, though. But
Right.
you have to kind of memorize.
So
Really. Yeah. And you know how to put the formal charge in the structure. Calculate the formal charge.
what is that again?
Well, so say you have a Lewis structure. So.
Oh, yeah, the formal charge inside the, right, yeah.
So oxygen's got 6 valence electrons.
Yeah.
So let's say oxygen is in a compound. And it's, forget about what the rest of the compound is. So oxygen usually has 6 valence electrons. So what do? You take the number of valence electrons it has, subtracting this, right? The total of the lone pair, which is 4, then you divide up the bonding electron. It'll be 1, 2, 3, 4, 5, 6. So it'll be 6, 1, 6, so it'll be 0. Right? So in other words, the pair of electrons in this bond gets split between these two to make the calculation. Right? Whereas if you're talking about how many electrons are in valence all its orbitals have to be 2, 4, 6, 8. It's got to fill all of its orbitals with fill, so to speak, right? Okay, that's it. So there's a difference. If the formal charge is calculated, you have to split these charges. You can't count them all, right? So if you had another situation with oxygen like this,
And then you get the formal charge,
negative one, right? This would be negative, and it's still got 2, 4, 6, 8. It still has the octet. So yeah, the formal charge. But now the formal charge is important because if you have different structures, you could give you different structures, different inner structures, and say which is the most likely inner structure. And that's the one where there's the least amount of charge separation. And also, let's say there's a negative charge that has to be put somewhere in there. That would have to go on the more electronegative atom. Right? Remember that? Right. Yeah. So there's knowing how to assign the formal charges is also important in picking which Lewis structure is the predominant one. There could be like 2 or 3 valid ones. They all have octets and they don't violate any rule, let's say. But one of them is going to predominate just because it minimizes charge separation. Right? Remember, all these systems that seek to minimize the energy. Right? It just takes energy to separate charge. Right? And also, you know, a bad structure is going to have like a lot of negative charge on at least the electronegative atom. That's not good. That's what I mean. So it just,
so it's going to want it down.
Yeah.
So that's a less stable.
right, right. So that's,
Okay, here's a question. We have C2H4, and he's asking what's the hybridization of the carbon atoms in this molecule. And we have choices of sp, sp2, sp3, esp3, d2, sp3.
well, you have to know, does he draw the molecule for you?
Yeah, he does.
And so this is what he's doing.
Right.
So, right, so what is what's going on with this, these hybrid orbitals? You have a px orbital, you have a py, you have a pz. So you could have no hybridization, you could have sp hybridization, which leaves you with 2 p orbitals out here. You could have sp2 hybridization, leaves you with 1. You have sp3, which leaves you with none. Now, how many electrons can this make? Or rather, how many orbitals does this represent? 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay? It's always a constant number. So there's 4 low ones, is what I mean. It's one hybrid orbital. I misspoke with it. I mean, it's just one orbital, but it's got 4 lobes. And each one can hold an electron, 2 electrons. So what you want to do is know how these look, what the geometry is associated with these. Right? sp3 hybridization in your mind, that makes the tetrahedral structure where all the bonds are 100.5 degrees away from each other. Okay? The sp2 makes a trigonal linear structure, okay, which is what you see here. In the ideal, these are 120 degrees. It's not in an actual molecule. Remember, 3 times 120 is 360 degrees. Right? Okay, so that's the sp2. The sp is linear. Okay, it's got 2 p orbitals. sp2's got 1 p orbital. So in the sp2, what the basic telling is, if something's sp2 hybridized, that means it can make 3 sigma bonds. Okay, that's what this is doing. 1, 2, 3 sigma bonds. And it can make an additional pi bond. Okay, so consider what's going on in this carbon. It's got these are, say, X, V, Y. It's got these, it's P, X orbitals in this, so we brought it together. It's made these sigma bonds. Okay? It can also make these pi bonds that have this available. Right? That's why there's a double bond. Right? So these are the, what I'm trying to draw here is just the px orbital. Right? Plus, minus, right? And it comes together, you have this. Right? Okay? That's what's represented there, the double bond. There's also the sigma bond in here. So you want there's a geometry associated with all of these, right? This is a linear geometry. This is 120 degrees trigonal plane. Okay. This is the 109.5 tetrahedral. Okay. Right. And so, what does this one look like? Well, that is what you see in something like this. That's a beam. That's an E there. There's SA. That's an A there. Okay. So this one, that's the hybridization of the carbon in this one. It's got two double bonds and a sigma bond. That's what that means. Right? So it's got two double bonds that would be two vacant p orbitals. Right? And that's 100. You think of this as having it's 180 degrees. This is 120. 120. So
even though in those two trigonal elements, right, still fall under S. Theoretically, you could have
each one of these is sp2 hybridized, right?
right.
And so the sp2 part means it can make 1, 2, 3 sigma bonds. This is what you want to catch. The sp2 part means that each carbon can make 3 sigma bonds. 1, 2, 3. It's just a trick. By looking at the test, this is 1 equals 2 over 3. 1 plus 2 is 3. Just like carbon, it's sp3 hybridized, it can make 4 sigma bonds, but no pi bonds. There's no vacant p orbital available, right? Okay? An sp hybridized carbon can make 1, 2 sigma bond, which is what you see here, right? Sigma bond. Okay? And it can make, sigma bonds here. Okay? There's 2 of them. Okay? So you get what I'm saying. Okay? So you have this sp hybridized. So each carbon can make 2 sigma bonds. Right? So 1, 2. 1, 2. You see that? And so each carbon can also make 2 pi bonds. And I'm not showing them, but they're there. There's a pi bond.
They're there in triple bonds,
So pretend this is in the plane. This is in the plane. This is a sigma bond. This is a pi bond. Okay. And these are like this, right? Kind of coming out of the wood. Right? But then there's also ones that are facing us. At 90 degrees rotated. So behind the carbon-carbon line, there's this cloud of, say, negative, and then in front of this carbon-carbon line, there's a positive. They're just rotating 90 degrees. That's what they are. So, you want to get this down. Now, they show more complicated things than this.
Okay. What would, just so I understand, what would boron with 3 hydrogens that be sp3? Because it would just be 3 sigmas, there's no pi.
Different kinds of reagents. So what did you ask me?
Boron, three hydrogen.
With boron, okay, 3 hydrogens. Boron got 3 valence electrons. Hydrogen got 1. Okay, you see the 120 degrees there? Okay, that would be an sp2 hydrogen. Because it makes 3 of these bonds. It makes 3 sigma bonds.
Okay.
But it has an available p orbital. It's because there's nothing in it, doesn't mean it.
Okay.
I mean, it does mean something because it's available to react. Okay. It means a great deal, actually. But you get my point. Now, the thing about it is, they do things that are a lot more complicated than what we just showed. So I just want to thumb through this. Is this in chapter 5?
I think this would be chapter 6.
Chapter
Or, no, I think, no, this would be chapter 7.
Oh, it's chapter 7. So you really want to look at this because there's actually more to it. There's a bit of memorization.
Yeah, yeah.
Because if you look, there's more than just SP, SP2, and SP3 on the orbital. If you look at page 277, there's SP3D, there's SP3D2. Look at those and count how many sigma bonds that contain. For example, SP3D, SP3D, how many sigma bonds?
That's 5.
5. So that could make 5. So then the geometry associated with that is you've got to think of something making 5 bonds. The example is PCl5. Okay. So they give an example of PCl5. So, and they tell you that it's trigonal. They tell you that it's trigonal bipyramidal. So you want to know these things because that would come up. So what is trigonal bipyramidal? Right? So you have this Cl here. Right? This is all in this in a plane. Okay, it would be,
Yeah, 3 in the plane, and then 2 at the pole.
right. Yeah, 3 to plane. This is supposed to represent a plane. It doesn't look like what it's supposed to represent, but you know what I mean. Okay, and so this is something you have to know. There's also sp2d2, it's 6. sp3d2, okay, that can make 6 sigma bonds. Okay, sp3d2, and that's associated with the octahedral. Right? In an octahedral so in an octahedral so you have some central atom. You got one going like this, coming up, and like this, this. Then into the board, then out of the board. That's an octahedron. Okay? So octahedron means there's 6, not 8. So the point is that there's some of this stuff that's it's qualitative, it's kind of qualitative in the sense that you really want to be careful with detail. Because it gets more confusing when you have to, it's not so clear when you have to also account for lone pairs of electrons. For example, they give you this XEF 4. I want to do this one, XEF 4. Let's think about this XEF 4. How many valence electrons in xenon? 8. Okay. So that means we have to count for 8. How many electrons in fluorine? 7. So that means 4 times 7 is 28. Right? So now we have 8 plus 28 is 36. So let's draw the Lewis structure. I'm not drawing any particular geometry. Right? I just want to account for electrons. So if I just put fluorine in there just any old way. Fluorine's almost always like this, right? So how many electrons have I accounted for? 4 times 8 is 32. Right? I've accounted for 32 electrons. Minus 32 means 4. That means I have 2 lone pairs. Now, what does that imply to you? I mean, those electrons got to go somewhere, right? I need a hybridization scheme that can handle 2, 4, 6, 8, 10, 12 divided by 2, 6, essentially 6 lows where these electrons can go, right? Even though there's only 4 sigma bonds, okay? So that means that I need a hybridization that's just like the hybridization that we showed previously. Right? We showed this sp3d2, and I drew this. It's gone now, but I drew the octahedral. So that's going to have the same hybridization as something that had something that had 6 sigma bonds, right? So the point is that you have to take into consideration the lone pairs too. You have to be able to draw a Lewis structure. You can tell you can do it right away with the electron. And so, and you can see xenon 2, 4, 6, 8, 10. He's got 12 electrons in outer shell. So far down, all these orbitals are available. It's out of the second row. It's way down. Xenon's flying. Yeah. So anyway, the point is you have to know how many electrons you're dealing with before you pick a hybridization. If you have lone pairs, you have to accommodate those low somehow, right? So that's why this is not.
I say there's a lot of qualitative stuff that you have to mean. There's a lot of stuff we don't actually figure, calculate numbers. There's still some stuff that still has to be looked at very carefully.
So that's the
You want to get those.
Right. That's exactly right. You would have it like, you want it, the lone pairs, you want as far away from, their electron density is broader, spread out than in a sigma bond, right? And so the lowest energy configuration keeps those lone pairs farthest away from those sigma bonds, farthest away from the greatest number of sigma bonds. Right? So it turns out it's almost always the case. If you put one pair up here and one pair down here, then in a plane, this is going back, this is coming forward. Then this pair, okay, is 90 degrees away from all 4 of these bonds, right?
This one came out now.
So, if you were to put the lone pair here, for example, this would be one of those. Let me double check. for example, you know,
All those fluorines are the same thing?
yeah, they're all the same. Where it usually comes up is,
And that's AX42, square.
yeah.
Yeah, but square plane, the balance cells have SP2, you know, how do you discuss,
You say this is square planar because you don't take into account those when you describe it.
Yes, because, yeah, SP3, P2, all six objects.
right? So you have to, what you got to do is,
Okay. Right. I'm understanding the translation.
See, the thing is this, is you could put these electrons, you just couldn't have these two electron pairs right next to each other.
Right.
That's the issue, because the repulsion of these being right next to each other would increase the energy of this. You tend to keep the electron pairs farther apart. Okay? And if you put one here and put, change the fluorines, it'd be in the same spot. Right? You'd have to keep the electron pairs. That's the issue. You couldn't put them right next to each other.
Right.
That's drug, right?
Right. And well, I was thinking, yeah, that's how I would go.
all right, so there's SF. Here's another,
Here's a better example. That's SF5. Better example, SF5. S has got how many valence electrons?
Sulfur is six.
So it's 6, right? 'Cause it's right under oxygen. Always remember that. So, and fluorine's got 7. That's 35. All right? So that's total is 41. That makes sense to you?
Okay.
Okay, we'll only put that 4 fluorine, that's why we got a high number. So that's 4. SF4 is really the example that it's going to illustrate. That's 28. 28. So now we are at now we are at 34. So let's just without considering structure, let's just write this. Put the sulfur in the middle. That's fluorine, 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 fluorine. How many? Fluorine's always going to be like that. So how many electrons do we count?
We've got two left over.
All right, so we have 2.
Wait, 1, 2, 3, 4. No.
How many do we count?
We accounted for
4 times 8.
yeah, 4 times
32.
Right.
So you're right, we got 2 left over. So then, all right. So what does this tell you about how many lobes you need? You need 5.
Yeah.
So we need 5 lobes. So we know it's not the same as before.
it's going to be something else. It's going to be something SP3D.
SP3.
That's completely, that's right.
SP3D. And once you've exhausted the SP3, you need another lobe to throw the D.
Right.
Once you've exhausted SP3D, you need another lobe, SP3D2. Okay. So this is the kind of, we need this hybridization for this. Now, the question is, how do you draw it? I mean, this one's actually more, is a better example than the one I just showed because it illustrates something important. So we got You've got 5 really lobes to deal with. You've got 4 of these going. Okay? And we should know that SP3D is what? It's a trigonal bipyramidal gem. So you have sulfur. So trigonal bipyramidal is going to be. Here's the trigonal part. This is supposed to be in a plane. Okay. And then bipyramidal would be, we have this down here. Okay, we only have 4 of these, so we put another one up here. And this is the one that is wrong.
So this would be that. No, because that one here goes into, doesn't go into the plane.
It goes down into the plane because if it's here, it's 90 degrees away from all 3 of these. Right? If the plane is here, it's just 90 degrees. So it's affecting 3 of them by 90. This one by 180 is nothing.
Right.
So the minimum energy is put it.
But it can find it's only has.
Because if you put it there, that happens to be lower because
It has 2 that are at the 90. So if you push those out.
right. So let me go here. Because that's a lower energy configuration. It's 2 to 90 instead of 3, and 2 to 120. Those are 10
Right.
They're not actually meant to be, because it gets bent out. But it is it's kind of something to memorize, right? Because it's not quite clear to me why that would be lower energy necessarily than. So anyway, and so you could be asked questions like, okay, is this angle greater or less than 120 degrees?
It's less.
It's less, yeah. And is this angle greater or less than 180?
Less
Yeah, I think it's more. It's bent. It'd be bent.
yeah, I was thinking on the other side.
Yeah, okay.
So,
So
yeah.
you get it.
But that, so you say, you would say it's greater than 180, right?
Yeah, I don't think that's.
Okay.
So the thing is, when you make a distinction, hybridization, then you become volatile.
Yeah.
Because
Definitely
that,
need to know that.
because you know, it's the structure or what is the trigonal bipyramidal, what's the IPV. Usually we put all these in.
Yeah, I've got, in my notes, table 6.1. Is that?
Table 6.1 is really good. Page 43. Electron group geometry, and it's got electron. You have to distinguish between electron group geometry and molecular geometry. For example, AX3 is a efficient molecule. So let's do an example of this. So if you had NH3, you got 5, 3, there's an electrons you have to deal with. I just dealt with 2, 4, 6. I got a lone pair. Okay. That means I need how many volts? For the, so that would be what? That would be SG3. So
That's not how you relate it. That's not how you,
This would be trigonal pyramid because it's these, these are kind of bent down a little bit. Yeah, not that much, but enough to be, that makes it a pyramid. So even though you use SP3, you don't have it, you're not
describe the molecular geometry, it's actually,
but
to describe the molecular geometry, you don't need to think about the electron pair.
Right, the SP3, that was one pair, square function.
No, no, no. No, that would be then not touching. Right.
See, that chart is it. There's another example here, SF4. That's not SF4, trivial bipyramidal. Look at just take account everything. Fluorine, all there. The molecular geometry. So, here's the thing. X up to
X, two, we got 8 plus 13, 22. There's 22 electrons here. We got xenon, fluorine, just out 16 electrons, so that's 6 out. 1, 2, 3, 4, 5, 6. 1, 2, 3. I need something that has can accommodate 1, 2, 3, 4, 5 pairs of electrons. That's
Okay. Right. The molecule, this would be bad.
It's just a linear. That's why I brought it up. That's a linear molecule. Oh, because when you actually draw it, it's got to draw like this, right? Because those electrons got to go up these. The electrons are in the plane. You want the lone pairs as far apart from each other as possible. They're in, all 3 of them go in the plane.
Oh.
Okay, and so it's actually a linear molecule. So this stuff is
Describing the molecular geometry is one thing. Understanding how all of the single ions long pairs are that's different. That chart we're studying because one, there's 3 things listed as octahedral electron by electron group. You would judge this geometry by taking into account the electrons. The lone pairs are usually octahedral. When you look at it and you ignore the lone pairs, one of them is a square pyramid, one of them is a square planet, one of them is octahedral. If you look at the last 3 images on the chart, it takes 244.
Yeah, very
So you have to, if you said, what's the molecular geometry? You say octahedral because you took into account lone pairs. That's wrong. For example, XEF4 is square planar.
Right.
Okay, so I got to call it quits now.
Yeah,
I hope that was.
yeah.
I hope that helped.
No, absolutely. Absolutely. Thank you very much.
Okay. Oh,
You just want to keep track of people calls.
Yeah.
Everything else. I just need the email.